Welcome to the Learning Assistant app YouTube channel. Today, we aren't just going to memorize facts for an exam. We are going to peel back the layers of the material world to understand three of the most fundamental players in chemistry: acids, bases, and salts. Imagine you are standing in a kitchen. You see a lemon, a box of baking soda, and a jar of table salt. To the naked eye, they are just ingredients. But to a chemist, they are a vibrant landscape of moving protons, shifting electrons, and delicate balances of power. Why does a lemon sting your tongue while soap feels slippery? Why does a bee sting hurt? And why does rubbing a certain leaf on it make the pain go away? By the end of this deep dive, you won't just know the definitions, you'll see the invisible chemical tug-of-war happening all around you. Let's start with our intuition. Long before we had fancy laboratories, humans identified substances by how they interacted with our senses. If you've ever bitten into a raw lemon or a green apple, you know that sharp, puckering sensation. That's the sour signature of an acid. The word acid itself comes from the Latin acidus, meaning sour. On the flip side, think about the taste of baking soda or the feel of soapy water. It's bitter, and it has a distinct slipperiness. These are the hallmarks of a base, also known as an alkali. But we can't go around tasting everything in a chemistry lab. That would be a very short-lived career. So, we use indicators. Imagine a chemical mood ring. Let's look at the most famous one, litmus. Watch as we dip a blue strip of litmus paper into this beaker of hydrochloric acid. Notice how it instantly blushes a deep red. Now, if we take red litmus and dip it into sodium hydroxide, a base, it turns a calm, steady blue. An easy way to remember this? Base starts with B, and it turns litmus blue. Beyond litmus, nature is full of these indicators. Look at this extract of red cabbage juice. In its neutral state, it's a beautiful purple. As we add acid, it shifts through pinks and reds. As we add bases, it moves through greens and yellows. Even the turmeric in your kitchen turns a deep reddish brown when it touches soap. This is our first clue that acids and bases aren't just labels. They are states of being that change the very properties of the matter they touch. But what is actually happening at the molecular level? To understand this, we need to look at the work of Svante Arrhenius. Imagine a water molecule, H2O. It's a stable, happy little V-shaped molecule. Now imagine we drop a molecule of hydrogen chloride, or HCl, into that water. Watch closely as the HCl molecule enters the water. It doesn't stay whole. It dissociates. It splits apart. The chlorine takes the electron and becomes a negative ion, but the hydrogen is left as a lone proton, an H+ ion. This tiny, positively charged proton is the soul of an acid. In fact, in an aqueous solution, these H+ ions don't like being alone. They hitch a ride on a water molecule to form H3O+, known as the hydronium ion. So, here is our first deep dive definition. An acid is a substance that increases the concentration of hydrogen ions when dissolved in water. Now, let's look at a base, like sodium hydroxide, or NaOH. When it hits the water, it also splits, but it releases a hydroxide ion, an OH group. This OH ion is what gives bases their characteristic properties. A base is a substance that generates hydroxide ions in water. But here's a nuance that often trips students up. What's the difference between a base and an alkali? Think of it like a Venn diagram. All alkalis are bases, but not all bases are alkalis. An alkali is simply a base that can dissolve in water, like a special club of bases that love to swim. Now that we have our mental model of H+ and OH ions, let's see how they behave in the real world through their chemical reactions. First, let's look at the reaction between acids and metals. Imagine we have a test tube of dilute sulfuric acid, and we drop in a few granules of zinc. Immediately, you see bubbles fizzing to the surface. What's happening? The zinc is essentially kicking out the hydrogen from the acid. The hydrogen atoms pair up and escape as hydrogen gas, H2, while the zinc joins with the sulfate to form zinc sulfate, a salt. How do we prove that's hydrogen gas? Watch as we bring a burning match near the mouth of the tube. Pop. That characteristic pop sound is the tiny explosion of hydrogen reacting with oxygen. It's the classic pop test. But acids don't just react with metals. They have a very specific interaction with metal carbonates and bicarbonates. Imagine you have a marble chip, which is calcium carbonate, and you pour some hydrochloric acid over it. You get a vigorous effervescence. This isn't hydrogen, this is carbon dioxide, CO2. Notice the setup on the screen. We take that gas and pass it through a solution of lime water, calcium hydroxide. See how the clear liquid turns milky? That milkiness is the formation of a white precipitate of calcium carbonate. If we keep passing CO2 through it, the milkiness eventually disappears as the precipitate dissolves into soluble calcium bicarbonate. This is chemistry in motion, a cycle of transformation. Now let's talk about the most beautiful reaction of all, neutralization. Imagine an acid as a source of H+ ions and a base as a source of OH ions. They are like two opposite poles of a magnet. When you mix them together, the H+ and the OH find each other. They bond instantly to form H2O, water. They effectively cancel each other out. The remaining parts of the acid and base, the metal and the nonmetal parts, join together to form a salt. Acid plus base gives you salt and water. It's a chemical truce. If you've ever taken an antacid for a sour stomach, you've performed this experiment inside your own body. The excess hydrochloric acid in your stomach is neutralized by the mild base in the tablet, turning the fire into harmless salt and water. But how do we measure the strength of an acid or a base? Not all acids are created equal. You can put lemon juice on your salad, but you wouldn't dare touch concentrated sulfuric acid. This brings us to the pH scale. The P in pH stands for potens in German, meaning power. It's the power of hydrogen. The scale runs from 0 to 14. 7 is our neutral ground, pure water. Anything below 7 is acidic. The lower the number, the stronger the acid. Anything above 7 is basic. The higher the number, the stronger the base. But here is the aha moment. The pH scale is logarithmic. This means that a pH of 4 isn't just a little bit more acidic than a pH of 5. It is 10 times more acidic. A pH of 3 is 100 times more acidic than a pH of 5. Small changes in pH number represent massive changes in the chemical environment. Why does this matter? Because life is a delicate pH balance. Your blood stays strictly between 7.35 and 7.45. If it moves even slightly outside that range, it's a medical emergency. Plants are just as picky. If the soil is too acidic or too basic, certain nutrients become locked away, and the plant starves. Even in your mouth, if the pH drops below 5.5, the acid produced by bacteria starts to dissolve your tooth enamel. This is why we use toothpaste, which is mildly basic, to neutralize that acid after a meal. Now, let's move into the final frontier of this lesson, the world of salts. Most people hear salt and think of the white crystals on their fries. But in chemistry, salt is a massive family of compounds. A salt is what you get when the hydrogen of an acid is replaced by a metal. Interestingly, not all salts are neutral. If you react a strong acid with a weak base, the resulting salt will be slightly acidic, pH 7. If you react a weak acid with a strong base, the salt will be basic, pH 7. Only a strong acid and a strong base create a perfectly neutral salt. Common salt, sodium chloride, NaCl, is the starting point for a whole industry of chemicals. Let's look at the chlor-alkali process. If we pass electricity through a concentrated solution of salt water, called brine, it decomposes. At the anode, we get chlorine gas. At the cathode, we get hydrogen gas. And in the solution, we are left with sodium hydroxide, NaOH, 3 incredibly useful products from a simple jar of salt. From here, the family tree of salts grows. First, there's bleaching powder, KOCl2. We create it by reacting chlorine gas with dry slaked lime. It's the hero of water treatment and the textile industry, using its power to oxidize and remove colors or kill germs. Then there's baking soda, NaHCO3. This is a fascinating one. When you heat baking soda while baking a cake, it decomposes to release carbon dioxide gas. Those tiny bubbles are what make the cake rise and become fluffy. But there's a secret. Baking soda alone can taste bitter. That's why we use baking powder, which is a mix of baking soda and a mild edible acid like tartaric acid. When they get wet in the batter, they neutralize each other, releasing the CO2 without the bitter aftertaste. Next, we have washing soda, Na2CO3, 10H2O. Notice those 10H2O molecules attached to the end. This is called water of crystallization. These aren't wet water molecules. They are chemically bonded into the crystal structure of the salt. Without them, the crystal would change its shape and properties. Finally, let's look at plaster of Paris. It's made from gypsum, calcium sulfate with 2 water molecules. If we heat gypsum carefully to exactly 373 Kelvin, it loses some of its water and becomes calcium sulfate hemihydrate, plaster of Paris. The hemi means half. It's a white powder that, when mixed with water, reabsorbs those water molecules to turn back into hard, solid gypsum. This is why doctors use it to set broken bones and artists use it to make casts. It's a material that remembers its past. We have covered a lot of ground today. We started with the sour taste of a lemon and the slippery feel of soap. We dove deep into the world of ions, seeing how H+ and OH define the very identity of a substance. We explored the pH scale, that logarithmic ruler of life and death, and we saw how the truce of neutralization leads to the incredible variety of salts that build our world, from the fluffiness of our bread to the strength of a plaster cast. Chemistry isn't just about formulas on a whiteboard, it's a language that describes how the world works. When you look at a bottle of vinegar or a piece of chalk, you're now seeing the protons waiting to be released, the carbonate groups ready to fizz, and the delicate balance of the pH scale. To truly master this chapter, you need to practice. Chemistry is a skill as much as it is a science. We invite you to download the Learning Assistant app. There you can find interactive online tests specifically designed for the 10th grade curriculum to help you practice these reactions and concepts. Use the app to revise periodically. Repetition is how intuition is built. Thank you for joining us on this deep dive. If this video helped you see the chemistry of acids, bases, and salts a little more clearly, please give it a like and subscribe to our channel for more comprehensive guides. Go ahead, download the Learning Assistant app now, and let's turn that knowledge into mastery. Until next time, keep questioning, keep exploring, and keep learning.